Discrete mathematics starts with logic because every proof you'll ever write in any branch of math is built entirely out of logical steps like these. A proposition is a declarative sentence that's either true or false, never both and never something in between. 2 plus 2 equals 4 is a proposition, but what time is it is not. Since it isn't true or false, it's a question. Propositions combine using connectives, and or not implies, and if and only if. A predicate, something like x is even, isn't a proposition on its own, because its truth depends on x. It only becomes a genuine proposition once x is pinned down, either by assigning it a value, or by quantifying it with for all x, or there exists an x. Two simple logical laws form the bedrock of everything else. The law of the excluded middle says, P or not P is always true. The law of non-contradiction says P and not P is always false. De Morgan's laws tell you how negation interacts with and or. Not, open bracket, P and Q, close bracket, equals not P or not Q. And the mirror version, not, open bracket, P or Q, close bracket, equals not P and not Q. Notice the pattern, negating flips the connective and becomes or becomes and. The contrapositive equivalence is one of the most useful tools in this section. P implies Q is logically the exact same statement as not Q implies not P. Quantifier negation tells you what happens when you push a not through a for all or a there exists. Not open bracket for all x p of x close bracket equals there exists an x such that not p of x. And negating a there exists gives you a for all with the inner statement negated. Let's prove the contrapositive equivalence properly using a truth table, since that's the most bulletproof way to confirm two statements are logically identical. Build a table with every combination of P and Q, true true, true false, false true, and false false. Going row by row, when P and Q are both true, P implies Q is true, and not Q implies not P is also true. When P is true and Q is false, P implies Q is false, since the promise was broken, and not Q implies not P works out to false too. When P is false and Q is true, P implies Q is true, vacuously, and not Q implies not P is true as well. When both are false, both implications come out true. Every single row matches, so the two statements are logically equivalent. Proof complete. Here's the intuition behind why implication works this way. Think of P implies Q as a promise. Whenever P holds, Q will too. The only way to break that promise is for P to be true and Q to turn out false. If P never happens at all, the promise was never tested, so it's counted as vacuously true. Here's a useful trick. For P implies Q, there's only one row you actually need to check, the true-false row, where P holds and Q fails. That's the only way to get a false overall. And if a direct proof of P implies Q looks messy, try proving the contrapositive instead, since it's logically identical, and often the algebra is cleaner. Worked example A, a direct proof. Claim if n is even, then n squared is even. Step 1, let n be even, so n equals 2k for some integer k, since that's exactly what even means. Step 2, square both sides, n squared equals, open bracket, 2k, close bracket, squared equals 4k squared. Step 3, rewrite 4k squared as 2 times, open bracket, 2k squared, close bracket. Since 2k squared is itself an integer, n squared equals 2 times an integer, which is exactly the definition of even. Proof complete. Worked example B, a proof by contrapositive. Claim, if n squared is odd, then n is odd. Step 1, look at the contrapositive of this statement. If n is even, then n squared is even, and that's precisely example A, which we've already proven. Step 2, since the contrapositive is true, and contrapositive equivalence tells us a statement and its contrapositive always share the same truth value, the original statement must be true too. Proof complete, and notice we didn't need any new algebra, we just reused example A. Worked example C, a proof by contradiction, the classic proof that the square root of 2 is irrational. Step 1, assume for contradiction that root 2 can be written as a fraction. are divided by b in lowest terms, meaning the greatest common divisor of a and b is 1. Step 2. Square both sides. 2 equals a squared divided by b squared, so a squared equals 2 times b squared. Step 3. Since a squared equals 2 times an integer, a squared is even, and by example b's logic, that means a itself is even, so write a equals 2k. Step 4. Substitute back in, open bracket, 2k, close bracket, squared equals 2b squared, so 4k squared equals 2b squared, so b squared equals 2k squared, meaning b squared is even too, so b is even as well. Step 5. But if both a and b are even, they share a common factor of at least 2, which directly contradicts our starting assumption that the greatest common divisor of a and b was 1. Step 6. This contradiction means our original assumption was false, so root 2 cannot be written as a fraction in lowest terms, so root 2 is irrational. Proof complete. Common mistakes to watch for. First, confusing implies with if and only if, since implication only runs in one direction. P implies Q says nothing about whether Q implies P. Second, when applying De Morgan's laws, forgetting to flip and into or into and, that flip is the entire point of the law. And third, proof by example. Checking just one case never proves a for all statement, no matter how convincing that one case looks. But flip that around, and it becomes a legitimate tool. One single counterexample is enough to fully disprove a for all claim.